Hello friends, in today's video we will learn about Planck's quantum hypothesis and how Planck was able to successfully explain the blackbody radiation. So before this quantum hypothesis proposed by Planck, the scientists were trying to account for the blackbody radiation and the blackbody spectrum based on classical theories. So two main theories that could successfully explain the blackbody radiation to a limited extent was Wien's theory and Rayleigh-Jean's formula. So Rayleigh and Jean. These scientists were able to explain blackbody radiation to a limited extent based on classical theories. For example, Wien was able to account for the blackbody radiation at lower wavelengths, small lambda. For smaller wavelengths, the Wien's theory could successfully explain the blackbody radiation and the different results that we see from the experiment. The Rayleigh and Jean were able to formulate a new formula which could explain the blackbody radiation at longer wavelengths. But both these theories, Wien's theory and Rayleigh and Jean's formula, fails to explain blackbody radiation in the full range. There were some discrepancies in explaining the blackbody radiation in all the lambda ranges for both the theories. What was the reason? Both the theories were based on the classical theories that were existing then. For example, in the case of Wien tried to explain blackbody radiation based on thermodynamic arguments, and he attempted to explain the special features of blackbody radiation based on classical thermodynamic picture. And he derived a formula, and according to the Wien's theory, E lambda d lambda was obtained as to be equal to 8 pi hc lambda raised to minus 5 e raised to minus hc by lambda kt d lambda, where E lambda d lambda is the energy corresponding to each of the wavelength, h is the Planck's constant, c is the velocity of light, lambda is the wavelength of the radiation, and k is the Boltzmann constant, T is the temperature, and so on. So if you try to plot this curve and try to explain the dependence of energy on wavelength based on this theory, you can successfully explain the blackbody radiation for small wavelengths and not for longer wavelengths. It will fail at longer wavelengths. Similarly, Rayleigh and Jean examined the problem and treated the radiation inside the blackbody as a series of standing electromagnetic waves. And they estimated the energy density, and they obtained the energy density to be equal to E lambda d lambda, the energy density corresponding to a very short range of lambda, is equal to 8 pi kt lambda raised to minus 4 d lambda. So this was the dependence of energy and lambda according to the Rayleigh-Jean picture. So both the theories were somewhat successful because they could account for the blackbody radiation at a very short range of lambda. Rayleigh-Jean's formula was successful in the longer lambda range, and the Wien's theory was successful at the shorter wavelength. And since both the theories were not able to explain the blackbody radiation, Planck tried to account for the blackbody radiation based on a new hypothesis. And Planck succeeded in deriving a formula which agrees extremely well with experimental results. So he discarded both the ideas of radiation based on the classical picture, that radiation is a continuous stream, and he also discarded the idea of law of equipartition of energy. And he proposed a new hypothesis called the quantum theory of radiation. And he proposed some basic postulates or assumptions in order to consider this new theory. And the basic assumptions of the Planck's quantum theory of radiation are: a black body radiation chamber is filled up not only with radiation but also with small harmonic oscillators or resonators of molecular dimensions, and they can vibrate with all possible frequencies. So when you take a black body which is emitting radiations out, and this black body should not be treated classically. Instead, this black body is made up of molecular harmonic oscillators, and these will be oscillating at a particular frequency, and they can choose all possible frequencies in order to vibrate. And the second assumption is that the oscillators or resonators cannot radiate or absorb energy continuously. An oscillator of frequency nu can radiate or absorb energy in units of quanta of magnitude h nu. So this is the second major assumption. First assumption is that a black body is made up of small oscillators that are oscillating at different frequencies. Different possible frequencies can be chosen by the oscillator, but if nu is the frequency of oscillation, then the energy of that oscillator can only be an integral multiple of h nu. It can be either 1 h nu or 2 h nu, 3 h nu, and so on, and it cannot choose an energy in between. So that is the basic concept of this quantum theory, that energy is not continuous and energy is discrete. In physics, quantum is the minimum amount of a physical entity involved in an interaction. So the fundamental notion that a physical property can be quantized is referred to as the hypothesis of quantization. The quanta simply means the basic unit of something, or how much, the minimum unit that can be chosen by a particle. In terms of energy means h nu is the minimum energy that can be radiated by a particle oscillating at a frequency nu. And these two assumptions acts as the basis of the Planck's quantum theory. This innovative idea that energy is not continuous and that energy is discrete and its basic unit is quantum or quanta given by h nu is of revolutionary effect in the field of physics, and plenty of other theories were later explained based on this single hypothesis. So as of now, we have understood that the black body radiation could not be explained under the classical picture, and the classical theory assumes radiation and energy changes as continuous. That means all energies can be chosen by an oscillator. And based on the classical theory, there were two distinct theories that tried to explain black body radiation. Those were Wien's theory and Rayleigh and Jeans theory. Both the theories were able at certain ranges of lambda but failed at other ranges. So Planck proposed the new quantum theory based on two important assumptions, and we studied those assumptions as the black body to be made up of small molecular oscillators oscillating at different frequencies, and that if the frequency is nu, then the energy is not continuous then the energy can be chosen only in units of quanta, and each quanta has a magnitude of nu. So that is the major concepts that we saw today. I hope this basic theory is clear for you. Thank you.